Hi everyone. Uh, in today's session, we will be making the mesh. Last time we finished the geometries using space claim, AutoCAD, and Creo modeling, and today we will moving towards the meshing side. Uh, in this program, I've already completed one of the mesh. This is the mesh that we will be making today, and we will import all the parts, make the named selections, and using different edge sizing, we will make this mesh. So, but in today's session, we will continue in a different. We'll start from an empty workbench project, and this is already being compiled. All these things are already compiled in the meshing part in the guidebook, so that's for better reference. And here we will actually, yeah, we need to define if it's solid and fluid zones, and after defining them, we can have the name selections. And as for this edge sizing, we will give two elements in the thickness of AFL, CFL and CCCL because they're very thin, so we need to manually give the two element sizing, and rest all will be 0.1 mm all the sides, and we'll finally make the mesh. So we'll start by using an empty project. I've already started an empty project, and using the space claim geometry, I need to import it. Even the space claim geometry is empty right now, so let's import the geometry so we can directly open the geometry. And from previously, we already know the previous workbench project that we made, the mesh is where we made all the geometries, is meshing demo. So in that directory, we will go and in the guidebook, and in the meshing demo files, we'll go to dp 0 system and open this. So we got the cell geometry now, and with this cell geometry it's already being shared. So if you go to the workbench and share topology, there's nothing to share. Okay, so there's nothing to share, and you can just directly close it, and we can start them with the mesh. Now this is the model that is being imported from the geometry, and we'll start with the meshing. So the first part that we need to define is the type of mesh that we have wanted, not for mechanical, we want for the CFD program. We already covered it previously, and for Fluent, and we'll set the default element size to 0.1. So this thing is very basic, and for the geometry we first need to set the fluid zones and the solid zones. So this is actually a node mesh. So we can rename it over here also, or create in the name selections. We will directly create the name selections, but since we will need to select the edge sizing, so it is better to rename here also. So let's rename, so mesh anode. The next is anode support layer. Yes, then the next is the anode active layer. Then we have the current active layer, cathode active layer. Cathode current collecting layer, and this is the mesh cathode. Now all these are renamed properly, and the next thing is that we should make the named selections also. So first we will make all the solid bodies as the named selection. So we'll start from the anode side, anode active layer. We'll create the named selection from started from here, and we call it AFL, that is anode functional layer. Then is the anode support layer. We can directly use tab N, press N, got the AFL. Then the anode support layer, press N, create named selections, ASL. I think we can only press when we select from here. Okay. After that we have CFL, cathode current collecting layer, mesh anode, then we have mesh cathode, interconnect anode, interconnect cathode. And now we want to make the define all the surfaces also. So we'll start by defining the wall electrolyte at the anode side. So for that we should hide all the geometries, and the electrolyte is actually between the active layers, so we will hide everything on the cathode side. So we should hide everything, and where is anode active layer, hide all other bodies. So the top side of the anode, that is actually the electrolyte surface. Create name selection, and we must name it with wall. Now let's show all geometry on these, and now we'll go towards the inlets and outlets. So at the anode side we have the inlet at the anode side in positive X direction. So we will select this surface, tab N, and this is inlet anode. And then we have inlet at cathode, that is in the positive Z direction. Now the outlet of anode, and likewise the outlet for cathode. Now after these name selections, the most important name selections are the voltage tabs and the current tabs. We should name them also. The voltage tab is on the anode side. We model the geometry with cathode on the top side. So on the top is the current tab, and voltage tab is on the anode side, is at the bottom. This is the voltage tab surface, and this here is the current tab. Okay. Now with this we have finished the name selection thing, and now we need to start with the meshing. So in the mesh we first insert the methods, that is the sweep method. With the sweep method is the first that we will have, and for that we should hide these bodies, and all these other bodies, they are good for sweep methods. So now there are overall one. So we'll insert the method, insert method, and go for body selection, control 6. So all these 6 bodies will introduce a sweep method. Okay, now we should include the edge sizing, and for the edge sizing, insert sizing, and towards the edge, these are the 3 layers that are most used. So we have 3 edges, and the element, not the element size, will have number of divisions, 2 divisions, and the had that it should definitely have a hard behavior to make these divisions. And no, not this one, this, and extend to adjacent. It's better to add single each. We have got 6 edges now. We need to do it for the other sides also. So we have overall 12 edges that have 2 number of divisions, and we set it to hard uh, biased. Go to the default setting, and on the other edges, edge sizes, we must have a fixed biased rules for 0.1 mm. That is also necessary. So we will have the edge sizing on all the other edges. So we should have insert sizing on the other edges. And so we have got only 4 edges, so we should actually extend by limits. On these 8 edges, these are so these are 8 edges, and we should add the other edges. So now there are total of 16 edges, and they have been okay. So now the edge sizing for the planar surfaces is done, so we can start meshing one by one. So we should select the mesh node or the smallest layer, start with the meshing, and we'll go by body select, and let's select not this one, this body. These bodies are planar bodies, so it should be meshed with no problems. And if we click on the mesh, we will be able to see the mesh. But now you see there are too many distortions available. You can see many distortions, so I think we missed hard to set it default to 0.1, and we need to set the curvature to no to make the behavior of the sizing as hard. And now we will mesh them again. Let's go to mesh. Now you see this is properly meshed, and so this we should generate mesh. I think this is okay. There's no problem with this. There shouldn't be any problem on this side also. Yes. And finally we can generate the mesh on the mesh at the anode side also. So as far as the planar surfaces are concerned, they can be meshed very easily, but we need to give the hard sizing, and we can see that all the mesh for the planar surfaces, they are done. Now the other remaining parts are the interconnects and the gas channels. Now we'll start by meshing the gas channels, and we will include them one by one. So we first show body, and for the gas channels we need to go for the multi-zone meshing. And so we import we introduce a method. We apply this one, and in the gas channels, both the bodies for the gas channels, and set them for multi-zone. And okay, minimum edge length 1 mm. Okay, that's okay. Okay, now let's try to mesh one by one. It takes quite some time for this meshing, so I will pause the video over here to save the okay. And if you go to the mesh, okay, now this is, yes, this is meshed, and likewise we'll mesh this one also. Yes. Now both the gas channels are meshed, and what it does is actually it divides into the multi-zone method, actually divides it automatically into different geometries and mesh them. So the last part are the interconnects, and for that we need to introduce another method, and we will include a hex dominant method. So we will introduce a method. Oh, sorry, we should include show body, and include the method. The interconnect bodies, we will apply the two bodies, and we will have a hex dominant method. Okay, now we should mesh them again one by one. It takes quite some time for the meshing of the interconnect because makes a lot of calculation for the hex dominant methods. And if you see the mesh now, it is properly calculated and properly meshed. And the last part that we need to mesh is the second interconnect at the anode side. So we will select it and generate mesh on selected bodies. It takes quite a while for meshing this body, and now it is being meshed. Now you see that we have a very good mesh for all the bodies, and we can see the statistics of our mesh. The total number of elements is about 2.19 or 2.2 million elements, and we should check the quality also. So we go to the metric graph and element quality. So there are few TET4 mesh also. So like probably during the meshing it included some meshes of TET4 and pyramids also, but overall it's a hex mesh. We don't have a perfect control in this type of meshing. We don't have a perfect control over the meshing methodology. That is much better control when we do the map meshing. So we will do that in the later video, or the next session we will discuss that. So for this time we have, but the element quality, the worst quality elements, you can see yeah, there are very small elements that are for TET4. It shouldn't be in TET4 elements at least. In the anode, oh, these elements are in the interconnect region. Although it was hex dominant method, but there can be issues. So we will, if we hide bodies and now check the mesh qualities. Now these are the worst meshes, even though they are hex mesh. These are have the worst quality meshes, and because they don't look anywhere near a hex. So now they can make some real issues when the flow is being solved in these regions. Overall the meshes have very high quality, but there are low quality elements as well. So we will address them in the next session when we move towards the map meshing. Now as far as this session, we can the mesh we have got obtained a very good mesh. You can close the matrix, and with around 2.2 million elements, so this is a very good quality mesh with a few issues at the gas channels, but that can create some solver problems when we move to the fluent problem. We will discuss that later in the next session. So for this, the mesh is completed and we can move towards the fluent part. It can directly, but we should update it. So it will transfer the mesh from the meshing program to the Ansys Fluent program. It will write the mesh for the Fluent. Now we can open. I would like double precision, and let's say 4. We only want to see the mesh for now. As you can see, the mesh is completely imported and there are no problems while importing the mesh from here. So you can have the colors by surface. Yes, so everything is being imported properly. There are no problems, and we can see this extends. So this is a very good from the modeling up to and meshing and import to the meshing. This has been a very good model because there is no very small inaccuracies present in the model. So that's all for this video. So we will meet in the next session. Thank you.